This lecture is part of an online course of multivariable calculus, and I'm going to talk about curl of a vector field. Okay, so let me start by a vector field in a space. So for a vector field F, which has the coordinates P, Q, and R, where P, Q, and R are basically functions of x, y, and z, we can define an operation that would be very helpful for definitions that we're gonna talk about. So I'm gonna introduce the operation which we call it Dell. So operation Dell has this notation, and it's a vector. Actually, it's kind of a notation wise, which the first coordinate of it is partial derivative with respect to x, the second coordinate is partial derivative with respect to y, and the third coordinate partial derivative with respect to z. Okay, now it looks familiar. It's just because del of f, when f is just a function of x, y, and z, this is gradient of a function, right? Gradient vector. Then we say del cross the vector field f. This is called curl of f. And del dot product with the vector f. This is called divergence of f. Okay, so we define two operations on vector fields. One of them is curl of f, the other one is divergence of f. I'm going to talk about divergence on the next video, but for this video we're going to talk about curl. And if we apply the del operation on a function, we get the gradient vector. As you see, the gradient of a function f would be partial derivative of f with respect to x, partial derivative of f with respect to y, and partial derivative of f with respect to z. This is called gradient vector of a function. So when we apply del over a function, we get the gradient vector of a function. Now let's see what's going to happen if we have the cross product of the operation del with a vector field. This is curl. And basically curl of a vector field f measures failure of conservativeness. Okay, so if you remember, we say that a vector field is conservative if f is gradient of a function. So let's see what it means. First, let me define the curl of f for just the vector field in a plane. So for a plane vector field, if we have a vector field with just two coordinates that is defined on a plane, then we say that the curl of f, that we show it by the del operation cross product with f, it's q with respect to x, which is the second coordinate with respect to x, minus the first coordinate with respect to y. Okay, this is actually a scalar quantity. It's not a vector. Scalar quantity. And you can remember it by writing it like this. Partial with respect to x, partial with respect to y of p and q. Okay, let me write this in here so that you see what's going on. Okay, let's find the determinant of these metrics. it would be what? It would be partial of q with respect to x minus this one, which is partial of p with respect to y. Okay, so this is curl of a vector field f that is defined on a plane. Okay, then if you remember, we said that the vector field f is conservative, which means that f is gradient of a function if and only if this is equal to 0. This quantity q with respect to x is equal to p with respect to y, which is basically saying that curl of f is 0. So if curl of f is equal to 0 when f is a vector field in the plane, then the vector field f is conservative. Now let's see what Green's theorem says. Look at Green's theorem. So Green's theorem says what? Says that the integral of f dot dr over a closed curve C. So C is a simply closed curve. It means what? Simply closed curve, it means that the curve is not like this. It's just like that. So simply closed, this is not a simple closed curve. This one is, okay? So a simply closed curve like this one, which is positively oriented. Positively oriented, it means that if we have, let me make it a little bigger. If we have this closed curve, it's the direction of it is counterclockwise, such that if you walk along C in the direction, then the region that is enclosed by C is on your left. Okay, so that's the region R. Okay, so Green's theorem says that the line integral of f dr over a closed curve C is equal to what? Let me move these ones a little bit. It's equal to the double integral over the region R, which is the region that is enclosed by the curve C, of what? Of qx minus py. Qx minus py, where p and q are coordinates of f. And this is basically curl of f, right? Curl of f dA, right? dA. And as you see, basically Green's theorem says that the line integral of f over a closed curve C is equal to the double integral of curl of f. Curl, as we talked about, is a scalar quantity. It's a function, it's not a vector. And then its definition is q with respect to x minus p with respect to y. Okay, so now that was definition of curl for a vector field in the plane. So in R2, we define curl like this, and we have the Green's theorem in terms of curl. But let's look at curl in R3. Okay, so in R3, curl is actually a vector quantity. Curl of f in R3 is a vector quantity. A vector quantity. And let's define it. So I'm gonna say that curl of f is equal to what? It's equal to the Dell operation cross product with f. It would be the determinant of this matrix. On the first row, I'm going to put I, j, and k. On the second row, I have the del operation, partial with respect to x, partial derivative with respect to y, and partial derivative with respect to z. And on the third row, I have p, q, and r. Okay, so this is how you should memorize that, or basically how to remember it. Now let's calculate this integral, this determinant. I have I, j, and k, so it would be I. Now I'm gonna remove the row and column containing I. I'm gonna remove the first row and the first column. I find the determinant of this minor. It would be what? It would be this times that minus this times that. So it would be partial derivative of r with respect to y minus partial derivative of q with respect to z. This is times I. For the next one, I have negative j, and I'm gonna remove the row and column containing j. So I have this one, partial derivative of r with respect to x, so partial derivative of r with respect to x minus partial derivative of p with respect to z. Okay, let me move this one down. Okay, and the last one, it would be plus k. And for the k, I'm going to remove the first row, the third column. So it would be partial derivative of q with respect to x minus partial derivative of p with respect to y. Of p with respect to y. And then k. Okay, so you might notice that this is the actual definition of the curl, but this is how we remember it, by finding the cross product of the del operation with the vector field. Okay, so you might observe that actually the k component, the last component, would be the curl in two-dimensional. So the k component is the same as curl as two-dimensional curl. Right? This is definition of the two-dimensional curve. So let me give you one example. The vector field f is this: negative e to the x y I plus x y z j plus ln x z square k. Okay, what is curl of f? Okay, so to find curl of f, I'm gonna say that I need to find the determinant of I, j, k, partial del operation with respect to x, with respect to y, and then with respect to z, and then negative e to the xy, and then xyz, and then ln x times z square. Okay, so let's write the components. The components for I would be derivative of that with respect to y, which is 0, minus derivative of this with respect to z. You see, it's xy. Second component has a negative sign, and then I'm gonna remove the row and column containing j. So it would be derivative of this one with respect to x. It would be z squared over x minus derivative of this one with respect to z. You see, with respect to z, it is 0. And then the last component is what? Derivative of q with respect to x minus derivative of p with respect to y. So I'm going to multiply this by that. So derivative of this with respect to x is yz minus derivative of this one with respect to y. You see? with respect to y, it is a negative e to the x. Okay, that's curl of f. So what is the physical meaning or physical interpretation? So as a note, if we consider the vector field, let f to be the velocity field of a flowing fluid, then we say that the curl of f is actually it's the spin of fluid particles. So which means that if curl of f is equal to 0, so the vector field f, or the velocity field, or I can say the fluid, is irrotational. That's the physical meaning of the curl.